we're going to discuss ionization energy and electron affinity in two separate lectures. While the authors say we'll calculate ionization energies, what we'll actually do is recognize the periodic trends to explain observed ionization energies. Specifically, we'll define ionization energy and learn how to rationalize the observed first, second, and third ionization energies for an element based on its position in the periodic table. The rationalizations are easier to make after a quick review of the periodic table, which we'll do throughout both lectures. Towards that end, we'll identify the metals, nonmetals, and metalloids to help us organize our thoughts on ionization energies and talk about how all elements want to have the same electron configurations as the noble gases. Let's begin. The ionization energy, which is the energy required to remove one electron from an atom, is always measured in the gas phase to limit the atomic interactions that would otherwise interfere with the measurement. Like the atomic radius, we see that the ionization energy is a direct result of the electron-nucleus interaction. As the effective nuclear charge, Z effective, decreases, atoms get larger and it becomes easier to pull electrons off. Removing a second electron requires more energy because now we're talking about taking a negatively charged particle away from an ion that has a positive charge due to the loss of that first electron. We can graph ionization energies as a function of atomic number. If we look at the first arrow, A, we see that as we travel down a group, in this case, the noble gases, ionization energy decreases, which makes sense. Larger atoms can't hold their valence electrons as tightly because those valence electrons are in energy levels farther away from the nucleus. If we look at arrow B, we see that ionization energy increases from left to right across a period. Taking a big picture view of these trends, we can say that the first ionization energy increases going from left to right and up a group or column. It's easiest to explain this in terms of decreasing atomic radius, but let's dig deeper for a moment. Recall that fully filled and half-filled electron shells are inherently more stable, meaning they are lower in energy. Not only is the size of the atom getting smaller as we move from left to right, but it becomes easier to gain electrons to achieve a noble gas configuration than to lose them. For this reason, you'll see atoms in the P3 column gaining 3 electrons, P4 gaining 2 electrons, and P5 gaining 1 electron, rather than losing 5, 6, or 7 electrons, respectively, to attain a noble gas structure. This is reflected in the trend towards higher ionization energies from left to right. In terms of types of elements, that means that our nonmetals tend to gain electrons to form anions, while our metals, on the left, tend to lose electrons to form cations. So how do we recognize the metals, nonmetals, and metalloids? Metals make up the majority of the periodic table entries and tend to be shiny, malleable, meaning they can be hammered into sheets, ductile, meaning they can be drawn into wires, and will conduct both heat and electricity. Nonmetals include the elements on the right-hand side of the periodic table, plus hydrogen. The nonmetal solids tend to be brittle, so if you hit them with a hammer, they're going to shatter. There are 7 metalloid elements that tend to share the properties of both metals and nonmetals. With this in mind, let's work through our first example. I've grabbed snippets of the periodic table to help us identify the elements in each set with the highest ionization energy. In set A, we see that potassium, gallium, and selenium are all in the n equal 4 principal energy level. Selenium is farthest to the right, and as a nonmetal in this position relative to the other elements in the list, will have the smallest radius and the highest ionization energy. In set B, oxygen, sulfur, and selenium are all nonmetals in the group 16 column. Oxygen, at the top of the group, will have the smallest radius and therefore the highest ionization energy. In set C, indium, arsenic, and chlorine are running roughly diagonal to one another from the metals to the nonmetals. Given that chlorine is the closest to the top of the periodic table, it will have the smallest radius and the highest ionization energy, as those tightly held electrons will be tougher to remove. In our graph of ionization energies as a function of atomic number, you may have noticed a few jagged steps in the general trends. Specifically, if we look at how the energy decreases going from beryllium to boron, we see that the first electron placed in the 2p subshell is easier to remove than the second electron in the 2s subshell. This makes sense because the 2s subshell is lower in energy than the 2p subshell. This trend is repeated going from sodium to magnesium to aluminum in the n=3 energy level. Another exception to the general trend in ionization energies involves paired electrons in orbitals. Oxygen has 4 electrons occupying 3 2p orbitals, so one orbital contains a pair of electrons which repel each other, making it easier to remove this electron compared to removing an electron from the half-filled 2p subshell of nitrogen. Now that we've explained these exceptions in the first ionization energies, let's look at the energy associated with removing a second or third electron. It's important to note that we don't pull multiple electrons off all at once. Instead, we remove them one at a time in the gas phase and measure the energy required to remove each electron. Typically, the ionization energy increases with each successive electron removed because we're pulling a negative charge away from an increasingly positive cation. Let's review some actual ionization energy values. If we review the ionization energies for sodium, we see that the first ionization energy is relatively low because it removes the lone electron in the 3s orbital. Once we go for the second and third electrons, however, we see a huge jump in the energy required to remove an electron because now we're digging into that filled 2p subshell with a noble gas configuration. The same jump in ionization energy is observed in magnesium. The 2 electrons in the 3s orbital aren't too tough to remove, but start picking at that noble gas core and it's going to cost you a high amount of energy. Let's look at another element. Where does the largest jump in ionization energy occur? Between the first and second electrons, or between the second and third electrons? Like sodium, the second ionization energy of potassium is much greater than the first because K+, with its electron configuration equal to argon, has a very stable electron configuration that is disrupted during its ionization to K2+.